We're going live. Oh, just a second. Okay, we are live now. So, let me welcome one and all for this edition of the NSF Wednesday Colloquium. It's a pleasure to have Professor Debashree Ghosh joining us, albeit online, from the Indian Association of Cultivation of Science for this session. Before I introduce Professor Ghosh, let me, just for those who are joining us for the first time, reiterate what the Wednesday Colloquium stands for us. So the Wednesday Colloquium is an interaction session within TIFR, within the Natural Sciences faculty, and it is as old a session as TIFR itself. In fact, our founding director, Professor Homi Bhabha, had the vision of starting this colloquium series with the idea that when we invite physically people to TIFR, two parts are served. One is, of course, the speaker or the expert sees TIFR as an institute. And the second one is it also sort of brings all the natural sciences faculty, be it physicist, chemist, or biologist, together, listening to an expert in any of aspects of natural sciences. And because the speaker puts the general tone in the lectureship, it allows for a very interdisciplinary discussion. And also that has enabled TIFR itself, because of a small institute, to have cross-collaborative efforts attempting important questions. So, so this has been a historically very important series. So we have an expert amongst us today, Professor Debashree Ghosh. So Debashree, welcome. Just before I sort of give you the floor, Debashree, just a quick introduction. So Debashree is actually a chemist by training. She did her bachelor's from Presidency College from 1999 to 2002. And then she moved after her bachelor's to Indian Institute of Science for a master's, which she carried out under the aegis of Professor Yashonath. This is where Debashree sort of dabbled into computations. And from August 2002 to July 2005. After that, she actually moved on to do her PhD and, of course, a master's that comes with it in Cornell University. And this she carried out from 2005 to 2009. And the sort of advisor she worked on was with Garrett Chan. She actually looked at advances in application of static and dynamic correlation methods in ab initio quantum chemistry. So this is where she sort of got trained in electronic structure methods. Debashree then went on to do a postdoc from University of Southern California. This was with Anna Krylov from 2009 to 2012. And after finishing her postdoc, she actually joined as an assistant professor in NCL, Pune, where she was there from 2012 to 2017, before she moved on to Indian Association of Cultivation of Science in 2017 onwards. And she's now a full professor there from June 2021. Debashree, of course, is well known within the community of electronic structure methods. But one of the most important things that she does is she looks at very large complex systems as and uses DMRG methods, which are which she will of course discuss in her talk, Because of her wonderful work for all the years that she has been in an independent position, Debashree was recently given last year the annual medal of the International Academy of Quantum Molecular Sciences medal in 2021. And this is a very prestigious medal because of her wonderful work. She was awarded. So Debashree, without much further, taking much further time from you, welcome to TIFR for this colloquium. And I hope we know that we'll enjoy it, and I hope you enjoy the feedback too. So, Debashree.
Thank you, Jyotishman, for the very kind introduction. You can hear me, right?
Yes.
Okay, great. So thank you for the introduction, and also thank you for calling me to this historic event. I feel very, very honored. Let's hope that I live up to the expectations. Okay, so as Jyotishman kind of pointed out before, I'm going to talk about strongly correlated electrons, and that too in excited states of chemical systems. And hopefully along the talk, I'll be able to explain why this is challenging and how some of these challenges can be circumvented. Of course, not all, otherwise the field would be done. So before I go into the meat of the talk, let me give a brief overview of what we do in our group. I'm mostly interested in excited state processes in biology, and most biological systems are actually reasonably large. Therefore, one cannot afford to do only quantum chemical or quantum mechanical methods, and therefore we tend to use hybrid QMMM methods for these problems. And therefore, the MM part of those QMMM methods is dealt with and developed by a fragment-based and machine learning-based polarizable force field, so that it can take into consideration all the minute effects of spectroscopy on the biological system due to the presence of everything around it. And by everything, I mean there's a whole lot of mess around all biological systems, right? So many amino acids, water, etc., etc. For the quantum mechanical part, we develop strongly correlated methods using the crutches of DMRG and tensor product states and so on. And the few of the interesting systems, well, at least interesting to us, systems that we apply these methods to are in understanding photoprotection in melanin and spectroscopic properties of fluorescent proteins and RNA and so on. Today, I'm mainly going to talk about the strong correlation part of the work, and with some small examples of certain applications that we have worked on. Let me first discuss a few of the examples where this will get important, this electron correlation and excited states. And I will show you the common theme among all of these seemingly very different looking problems. One of the problems we are working on quite actively is in singlet fission. So what happens is when a chromophore is excited, it goes from the, let me get my pointer. Okay, it goes from the purely ground state to an optically allowed state of one or the other of the chromophore. I've just named it arbitrarily, right? There are, let's say, n number of chromophores, and one of them gets excited. Then what can happen in especially material systems where there are many monomers next to each other is this singlet state can actually bifurcate into two triplet states. And originally, we would think that a singlet to triplet transition is not allowed, and therefore we'll think that this won't be a big occurrence. However, if you look at the two triplet states over here, it's actually spin paired in the sense that one triplet is both down and the other triplet is both up. And so what that means is the total spin, total process going from here to here is actually a spin allowed process. If I look at the potential energies of these processes happening, I essentially start from a ground state potential energy surface, from the minima of that ground state, shine light on those chromophores, and those chromophores get excited into the optically active excited state, which then decays into a triplet pair state. So the question we ask is, what is the mechanism of these electronic structure of these states that are involved in singlet fission? And you will see that it involves not only understanding what is going on in the ground state, but the various excited states that may be in the vicinity of that optically allowed state or the TT pair state. So this is essentially what we need to understand, the electronic structure of many states. Similarly, in biology, when we are talking about photoprotection, and especially in the context of melanin, this is the spectrum of melanin shown over here. So melanin is formed of monomers. It's essentially a heterogeneous polymer, and the monomer is dihydroxyindole. The monomer spectrum looks exactly like what any other organic molecule will look like. There are peaks and then flat areas, and then more peaks.
I have one question on your previous slide.
Previous one?
Yeah.
Yes.
As just curious, so when singlet becomes triplet, in your cartoon you showed that the last part is somehow twisted, right? In the cartoon, at least from yeah, I see the last.
Yeah, sometimes and many times the geometry also changes somewhat. That is what is shown. That is, it allows for the change in geometry, whatever may be, but necessarily that's not necessarily true.
Oh, that's not necessary. But
no.
Like the question I wanted to ask is, what is the driving force for this twisting or change in the morphology of the molecule?
Well, I can give you a very simple example from the figure on the right hand side. See, the ground state geometry. Let's say this is the twist direction. Okay, so once you shine a light, it goes to the excited state, but it will slowly relax into the lowest vibrational state of the TT pair state. Or, I mean, it will first start to go towards the lowest vibrational state of the S1 state, and then whatever intermediate states, and finally the TT states. So if the twist direction was along this coordinate, it will twist. So that's what's essentially driving it. But it's not necessary, because again, it might not have been along this direction. It could have been right on top of each other, and then there would be not so much geometry change.
Okay, thank you.
Yeah. Okay, so as I was saying, in the photoprotection via melanin, melanin is formed of the monomers DHI. And the DHI spectra looks pretty normal for any organic molecule. But once I go into a melanin form, as in we have this heterogeneous polymer, it's a very fat, flat spectrum. There's no features whatsoever. And the main question that's bothering many people in this field is, why is this spectra so featureless? What part of the spectra is due to what part of the structures of melanin, and so on. And this problem is compounded by the fact that the final structure of melanin is a heterogeneous mess, and it is actually not known to people what kind of a heterogeneous mess it is. So these answers become quite difficult from an experimental perspective. Another question, which of course I am even more interested in, is what happens when melanin does absorb the UV visible light. So this is the spectra. So of course it absorbs all light that is incident in the visible 400 to 800, and even before in the UV region. So all that light gets absorbed, then how does it quench it? Of course it quenches it, because otherwise melanin would be damaged, and we would have horrible side effects in human bodies and so on. It doesn't happen means it quenches it somehow. So what is the process that leads to this quenching of that energy? And again, you see there are these various features of the excited state. This is just a cartoon. So there's these very, very many features of the excited states, and you can go from one excited state to another, and finally to the ground state via these various processes that can happen. Another problem we have very recently started dabbling in is light-induced spin crossover. So spin crossover molecules are sometimes, single d orbital metal with some ligand. It could also be a very long material system with many d orbital metals and ligands that are kind of bridging in between these metals. And the change in the and when light is incident in these on these molecules or materials, basically there's a marked shift in the electronic structure or the spin of these materials. So what happens? In line with the same question is, how do we even explain molecular magnets and spin states in general? So this is actually a very pretty molecular magnet, MN84. And I mean, how do you even begin to find out what is the electronic structure of each of the states? And here by electronic structure, I probably mean just the spin of each of the states that are possible in the low-lying states. So these kind of questions, you see there's a common theme that these all deal with one or more of the excited states. These excited states are almost invariably very low-lying excited states, so ground state, very near to the ground state. And because these many excited states come closer to each other, cross each other, there are vibronic features that take part in these states. There's even some singlet triplet crossovers, singlet triplet crossings, and so on. So all in all, this is actually a mind-boggling many different processes that are happening. And in order to understand that, people mostly rely on a combination of spectroscopy and computation. And here the computation mainly deals with the dynamics of the process, because once you excite from the reactant, this is the reactant potential energy surface, into one optically active, nearest optically active excited state, it can go via this direction or that direction and so on. So there's a dynamical process that is happening throughout, and it's like in each snapshots of those dynamical process, you are trying to understand the electronic structure of all the states that may be involved. So that's essentially the whole process that we want to target. Today, I'm going to talk about mostly the electronic structure part of it and why these electronic structure, these states are so difficult to compute, or so difficult to understand, as opposed to some of the ground states that are, kind of routinely done these days. So to begin with, as I mentioned, we need to look at the electronic structure of the ground.
Debashree,
yes?
Sorry, can you go back one slide?
Sure.
Yeah. Could you, for the sake of students here, could you just go through one of the arms of this, what kind of things you've shown here? So you have these diagrams like conical intersection.
Yes.
You have these cones shown.
I will explain.
Yes. Yeah, thank you.
Sure, no problem. Absolutely.
Yes, that would be helpful. Yeah.
Okay, so actually, why I can go through both the arms. That will be kind of instructive, I think, at least to the students. So this is, of course, this is the reactant minima, so the ground state, most stable state. And if you are going to excite a molecule, it will be from here on an average. And this molecule gets excited into the optically active state, which is the S2 state over here. Now, if you see, the S2 state actually intersects with another state, S1. This S1 state was beneath the S2 state, so chances are this was a optically dark state, and that's why it could not directly pump these reactants into this state. So you see these two states come towards near degeneracies at this point. And in these near degeneracies, we have drawn these fancy conical shapes. It's because if you look at the surfaces, the degeneracy is over 3n minus 2 degrees of freedom. And only in those 2 degrees of freedom, the degeneracy is lifted. So basically, if in two directions like a plane, if the degeneracy is lifted, you will have various kinds of cones. They don't have to be all sharp cones. They could be flat cones, like over here. They could be tilted cones like over here, depending on how the potential energy surfaces are, how they intersect with each other. But they'll always take the form of these conical shapes, no matter what. So that's basically these three structures in these three places. And then again, you can have similar crossings. Here, it won't be a cone anymore. This is a singlet triplet crossing, because here the degrees of freedom are quite different from a singlet crossing. And you could have intersystem crossing, you could have singlet triplet crossing, and so on. And finally, you will have a photoproduct The photoproduct could be this one also. Otherwise, it could be a photoproduct which is stable at some other geometry far away from the original geometry. For example, there could be a ketoenol tautomerism around here. There could be a triplet product that can be formed over here. There can be, any number of things that could go on because of the shape of the potential energy surface and the tilts of the potential energy surface. It can go from one kind of a structure to another. See over here, along the ground state also, this reactant to photoproduct, there is some kind of a barrier. This is completely the ground state, the green one. So here there's a big barrier. But if you somehow were able to pump this amount of energy using some laser pulse or whatever, then after that, you don't even have to worry about that reaction anymore. It will happen spontaneously, of course, after you have kind of pumped in so much amount of energy into it. There's no free lunch. You are still pumping the energy. It's not in the form of heat. Now it's it's in the form of light. So that's all the processes that are going over here. And there's also fluorescence and phosphorescence along the way, the processes that you have all looked at from the Jablonski diagram that you have studied. Okay. So this is essentially this plethora of processes is what we want to target. And the way to do that is, of course, to look at each snapshot, meaning each of these slices of geometry. So this is like a geometry parameter. This is some other geometry parameter going along. So these are reaction coordinates, right? Some complex bunch of geometry parameters. Along those geometry parameters, if we look at the electronic structure of the ground and the excited states, low-lying excited state at each instant, that is essentially the problem. Sorry, I basically have a call coming. I feel I have to take this. I'm very, very sorry.
Okay, that's okay. That's okay, Debashree.
Hello?
Unmute yourself, Debashree. Yes, that's fine. Yeah. Is everything
I'm
okay?
extremely sorry.
Is everything okay?
Yes, everything is fine. Okay. ACRB calling me, so that's why.
Okay, sure.
Sorry. Okay. So, so basically, we have to find out the electronic structure of the ground and excited states at each instant. Now, how do we go about doing that? Firstly, we will start with the Born-Oppenheimer approximation, which basically says that since the atoms or the nuclei are so much heavier than the electrons, at each instant of time, I can think of the atoms as not moving. This kind of counterintuitive, because on the one end, I'm saying dynamics, on the other end, I'm saying the atoms are not moving, but then I'm kind of freezing it at each time and looking at the snapshot. It's like a still picture. Of course, that still picture, if you put all the still pictures together, you will get a movie out of it. But for each still picture, I consider the Born-Oppenheimer approximation so that I can solve only the electronic problem separate from the nuclear problem. That's the first approximation. The second approximation that we typically take is a mean field approximation, by which we define orbitals and we solve for these orbitals, which are one electron wave functions, using the Hartree-Fock self-consistent field theory. From that, of course, we have to add some perturbative correction because, of course, the electrons are not, it's not that they are not correlated. It's not true that they are a mean field, the rest of the electrons, right? So to correct for that effect, we take some kind of a perturbative approximation. We call it either MP2 or CCST. Very soon you'll see there are very many alphabets coming up across. Don't worry about the alphabets. I'll explain what the essence of that method means, not what each of the specific method means, because that hardly matters in this context. So let's see whether this single reference method is actually adequate, because note, this single reference method is actually quite routine, and this is routinely done for all the ground state problems, many of the ground state problems, quite robustly. So what are the problem with these single reference methods, and why do we need to develop new methods for excited states? Let's take a simple molecule, water, and pull its bonds apart. So I'm basically elongating the OH bonds of the water molecule. And along this curve, I have drawn the distance between the O and H and the energy. The black curve is the exact curve. This is exactly how what you would expect, that if you pull the bonds apart, the energy will increase. And then finally, at one point, they will become just 3 radicals rattling around. And those radicals will have some energy. It will just be, it will plateau off. There won't be any change in energy after a point. This is the exact curve, the black one. If we use one of those perturbative schemes after single reference, such as MP2 or CCSD, this is what these curves look like. And that's quite wrong. I mean, qualitatively wrong, quantitatively wrong, everything a mess. And if you look at the errors, this is what the errors of the MP2 and CCSD with respect to Hartree-Fock looks like. So at infinite separation, where the reaction in fact is happening, you have infinite error, which is pretty disturbing, right? So this was for a bond breaking problem. The same kind of effect, unfortunately, shows up in excited states, in radical systems, diradicals, triradicals, transition metal complexes, polyenes, metal clusters, and a whole lot of other systems. And the reason why this happens is because of strong correlation between electrons. It's not weak correlation anymore. It cannot be dealt with perturbatively. Perturbation, as we know, by definition, can be used when the perturbation is small. If the perturbation is large, of course, everything is going to fall apart and the answers are just going to be totally wrong. So what is going on? Well, there are 2 effects that are going on. Firstly, the electrons will try to, or the orbitals which contain the electrons will try to delocalize and take as much space as possible. On the other hand, there's not just one electron, right? There are many electrons that are moving around. So these many electrons will try to avoid each other. So there's this really complicated stuff going on. And this is essentially what correlation is. And if I look from an energy perspective, so basically we are used to this orbital picture of looking at molecules, a single reference or Aufbau principle following one, where if you have n number of orbitals and m number of electrons, you populate till the HOMO, and from the LUMO onwards, everything is empty and things are, nice. We are used to this picture. But what happens when the energy gap between the HOMO and the LUMO becomes too small? At that point, essentially, it's not that only the HOMO can be doubly occupied. There can be electrons that are present in the LUMO or LUMO +1 or wherever. All those orbitals that are quasi-degenerate, basically meaning their energies are too close to each other in the valence space, all those quasi-degenerate orbitals can be populated by electrons. And in such a situation, we don't have a single reference picture, but rather many different reference structures of electron configurations. And that's why it is called multi-reference or multi-configuration situation.
There's a question that Chandan is asking. Chandan, could you unmute yourself? Chandan,
yeah, sure. So I have the question, like, what is the perturbation parameter in this case? And
the perturbation is the electron correlation. See, when we took the Hartree-Fock approximation, we had originally said that one electron I'm taking explicitly, all other electron I'll take as an average. That's not true, right? Electrons are not average. Electrons are really like n-1 electrons. And that's the approximation. That is the difference. So that is the V term, the perturbation term.
Yeah. So the following question which I have is, like, as the R is increasing, then the perturbation strength should be decreasing, right? Because it is like E square by R. And as the R is increasing, the perturbation strength should go down. So with increasing R, why the...
There's a very
Why
good
the
question,
model is not
because at
working?
that point, what is happening is, see, you had started with these orbitals, right? But these orbitals, if they come very close to each other, especially in the HOMO-LUMO, that is what is going, when you pull apart a bond, your HOMO and LUMO are not, are quasi-degenerate at that point, right? Because they are becoming more AO-like.
Okay.
Okay, so in that situation, you don't really have a very good description of the HOMO as you have solved for. In other words, you can't distinguish between the HOMO and the LUMO anymore. You
Okay.
can't say that HOMO belongs to the occupied space only and the LUMO belongs to the unoccupied space only. Rather, you are having a kind of a mixed picture of the HOMO and the LUMO both being somewhat populated, not doubly occupied or zero occupied, but something in between.
Right. So rather in this case, then this Born-Oppenheimer approximation has itself not valid, because like we have gone so far in the distance. So that is creating this.
No, that's not quite true. Born-Oppenheimer approximation has its problems, but that's not due to strong correlation. Strong correlation is simply an electronic effect, because the atoms are still fixed. There's no problem there.
Okay, so this r-axis which you had on the like x-axis, this r distance, that is the distance between the OH and the H, right?
It's O and H.
Okay. If I have question, I'll ask later.
Sure.
Thank you.
No, these were very good questions, and these have confused people for quite some time. Yeah. So should I go on?
Yes, sure. Yes.
Thank you.
Okay. So kind of to tie all of this together into a kind of a textbook-like picture. So this is a picture that we have seen in the textbook for the single reference methods. On the one hand, you have these various alphabets which are increased in the correlated methods, as in better and better correlated methods, till you have full CI, which is exact within that basis set. And on the other side, you have the size of the basis set that is increasing, which basically means instead of taking only the 1s orbitals, maybe I should take 2s and 2p, maybe I should take 3s, 3p, 3d, blah, blah, blah. If I keep increasing like that till complete basis limit, and if I take all possible configurations in that basis, that would be the exact, correct, foolproof answer, of course, with Born-Oppenheimer approximation. So now we can kind of create the same kind of a hierarchy for multi-reference quantum chemical methods. Over here are the single reference methods, and on the top you see these are the multi-reference methods. And I should explain these static correlation and dynamic correlation, these two terms, because these might be used again. So mostly what I call strong correlation, or the correlation due to orbital degeneracy in the valence space, that's static correlation. And mostly the correlation that can be taken care of perturbatively, some form of perturbatively, is the dynamic correlation. It is due to the dynamical dance of the electrons. So you see, if I take all possible configurations in the valence space, which I'm going to also call the active space, I have a method which is a self-consistent field, SCF method, but now it is a self-consistent field method in the complete active space, so CAS, okay. So instead of Hartree-Fock, which is a self-consistent field with a single reference, this is a self-consistent field with many references. And then on top of it, if I keep adding perturbations, I will finally reach to the exact answer like so. So this is essentially the kind of a map of the multi-reference quantum chemical methods that there can be traditionally. Now let's see even whether these traditional methods are good enough to take me to the exact solution, or whether I need that exact solutions even. And to kind of carry forward that argument or that point, let me take the example of acenes. So the singlet triplet gap of acenes. Acenes are these molecules, naphthalene, anthracene, tetracene. If you keep increasing, all of these are called acenes. So in 2004, DFT studies predicted that as you increase the size of the acenes, as you make it into 10 acene or 11 acene and so on, there is a singlet triplet crossover, in the sense that the triplet state now becomes more stable than the singlet state. In 2007, it was shown using DMRG that there is no such crossover, and the reason that there is no such crossover is because of static correlation. It is the correlation due to near degeneracy of orbitals in the valence space. In 2010, a dynamic correlation method was used to show that, okay, there is no crossover, but it is due to dynamic correlation. And in 2015, we showed from our group that both static and dynamic correlation is important. So it seems like wherever you shine a light, you see a problem, and then you say, oh, it is because of that problem. So this is becoming a bit bothersome, right? So why is it becoming, so first question is, why is it so difficult to compute this system? It seems like a pretty simple one. There's only carbon and hydrogen, no complicated stuff, no metal atom, no d orbital, nothing like that, right? The problem the reason why this problem is still challenging is because the number of configurations, you remember those different ways that I can put the electrons in the valence space, that itself increases exponentially with the valence space. So if the size of the valence space is large, the number of configurations or number of reference structures you can form becomes too large. As an example, let's say I have a polyacene which has 30 pi orbitals with 30 electrons. It is not that big of a system, because if you have 30 carbon atoms, it will have 30 pi orbitals. That CSF space, already the size of it is 10 to the power 33. So if I somehow created that 10 to the power 33 space, I don't know which computer I will store it in, but let's say I could store it in, then I did a matrix diagonalization of that size, I would require 10 to the power 99 operations. Just to put this thing in perspective, the number of atoms in the universe is 10 to the power 82. So there is no way how big a computer I can build up. I will never be able to solve this problem in a classical computer. But all I have in my lab is a classical computer. So let's see how to circumvent this problem. Before I go into circumventing this problem, let me explain this problem once again, because the exponential increase in the Hilbert space is not something we always have conceptually at the back of our mind. Let me take a simple example of a spin state. In each of these sites, so these are, let's say, like sites, and on each of these sites, there is a spin. That spin can either be up spin or down spin. So if there are 3 such sites, there are 8 such possibilities, like down, 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 up, like that. And if you notice, this 8 is nothing but 2 cubed. So essentially, if I have n such sites, it will become 2 to the power n possibilities. So my system size is now at the exponent. So that's an exponential scaling. So the Hilbert space is indeed increasing exponentially. And therefore, the full CI wave function I can write as something like that, where I'm summing over all possibilities. This is where the sum over is where this exponential scaling comes from. If I talk about in the matrix product state language, which is something I'll explain and use, this is what the full CI wave function looks like, where each of the tooth of the comb is like the physical dimension. Physical dimension meaning whether the spin is up or down, or whether the orbital is 0 occupied, as in unoccupied, or 1 up occupied, 1 down occupied, or W occupied. So these n are these physical dimensions. And this blob is the blob which is of a dimension 2 to the power n in this situation. So let me set a stage for the language of matrix product state. In this language, a real or a complex valued number, a single number, is defined as a round sum circle. The colors are immaterial. Colors are because I like colors. A vector, on the other hand, is round with a dimension, with a hand sticking out. And the hand is basically the dimension which has the index I. So that is why each of these hands are various dimensions. So psi, which has a dimension of n1 and n2 and n3 and so on. So if it had only one direction, one dimension, that is a vector. If it had two, in the same way, it's a matrix, it will have two hands. If it's a tensor of 5 dimensions, it will have 5 hands. So now in this notation, if I were doing a matrix vector multiplication, so this is my matrix M, which has 2 hands, and a vector V, which has a single hand, but the hand J is getting contracted over or summed over. Therefore, that is connected to each other. So there's like a handshake over here, and that dimension is getting removed because you are summing over that, and that dimension is getting removed. Similarly, if you are trying to find a trace of either a matrix or a product of matrices or whatever, then you would just sum over that other remaining dimension, right? So there will be no sticking hand. After tracing, you should get a single number. So you shouldn't have a hand that is sticking out. So this is what a trace will look like in this language. So now in this language, I have this full CI wave function, which is this strange kind of an object, this oblong shape with many hands sticking out like a comb. And each of these hands I have mentioned are the physical dimensions. Each of these physical dimensions has dimension d, 2 in case of spin, 4 in case of orbitals, and so on. So the total number of dimension of this object is d to the power n, which is an exponential mess. Now let me try and simplify it. In order to simplify, I can use a cool math trick called the singular value decomposition. If I do a singular value decomposition over here, where I'm taking all the directions in one side, all these indices in one side, I flattened it out, and the other direction is just this one, then what it will look like is this. So this is a matrix now. This is another matrix, but this is a diagonal matrix. Singular value decomposition, if you remember, is nothing but a more general kind of a eigenvalue problem, right? Where you can find the sort of eigenvalues of a rectangular matrix. Rectangular because, you know, sizes can be different in 2 directions, right? So I have no control about the size. So I can't make it a square matrix. So this is the singular value decomposition going on. And if I subsequently keep doing many singular value decomposition, I can reduce the dimension of each of the objects sitting on each of the sides and therefore get an exponential saving. If you look at the total number of matrix elements in this object or tensor elements in this object, the total number is n, which is the size, times d, which is the size of the physical dimension, times m squared being the dimension of the, the bond dimension that is saved in between.
So, Debashree, I have a question here.
Yes.
So, is this generally valid, or do you need some sort of sparsity in the?
This is generally valid. The m can become very, very large if there is no sparsity, and then you will get no saving.
I see. Okay. Thank you.
This is always valid because if I have a rectangular matrix, I can always do a singular value decomposition. If the singular values do not decrease quickly, then I have retained all the singular values and I have no saving.
I see. Okay.
Yeah.
Thank you. Thanks.
Okay. So on the other hand here, so this was the full CI wave function. This picture over here, if I write it out in the notation of algebra, this is what it looks like. So you have a matrix multiplied by a tensor, multiplied by a tensor, blah, 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 finally multiplied with a matrix. And this is, of course, an approximation because at each step, I'm not going to retain all the singular values. I'm going to retain only the important singular values so that I have some saving. A nice way to solve for this matrix product state, because here it is simple to show that we can find a matrix product state. I can't find this, so I can't do a singular value decomposition on this, so I can't find this matrix product state. This is something that I've just shown conceptually. So I have to have a way of finding these matrix product states without first finding the full CI wave function. Density matrix renormalization group gives us a nice way of achieving just that. And again, I'm going to explain in a very cartoonish fashion what DMRG does. I'll take the same example that we took before of the spin states. Each of the spin states can either be up or down, and therefore there are 8 possibilities in these 3 spin sites. Now, instead of going up to these 8 or 2 to the power n possibilities, if I look at just the 2 states, 2 sites next to each other, create all the states that are possible on those 2 sites, look at these, or rather look at their density matrix, and then retain only the few states that are most important. And this is where the singular value decomposition is happening. So now I have again reduced the degrees of freedom of this supersite. With this supersite, now if I increase the degree of freedom by taking into consideration the next adjacent site, I'll again increase the degree of freedom, look at those states, create their density matrix, diagonalize their density matrix, and retain only the most important states that are possible in those few states. So I have not let the number of possibilities increase limitlessly. I have actually kept them down to something something reasonable. This is not constant. By the way, here in the cartoon, I've shown that it remains just 2. That's not what it happens, but it's kind of kept constant at some m. That is the m states that are possible. Okay. Now let's look at what the wave functions look like algebraically. This is what the full CI wave function looks like. This is the Hartree-Fock wave function, which has no correlation between sites. So they are just products of sites or products of orbitals, of course, anti-symmetrized. And in case of DMRG, this is what the wave function looks like, where you have a matrix multiplied by a tensor, and so on. So essentially, DMRG gives us a simple algorithm.
Debashree, there is a very nice. We are going through very nice description now. There is a question from Pulkit. Pulkit, could you ask? Yeah, hi. So my question basically is that in the previous slide, when you showed those DMRs, so this one. So essentially, this final, by eliminating all the possibilities, you are trying to make a single reference state. No, I'm trying to make the multi-reference state, but not too much multi. I'm not keeping all the states. I'm keeping only the important states. One way to find the important states is to create all states and then look for the important states in it. The other way is to just go from one side to the other, creating all states of 2 sides only. 2 sides has only 4 states, right? So if I find out the most important states among those 4 states, retain a few of them, throw the less important ones, and then again take all possible combinations with the next one, and so on. That is why I mentioned that it's not that only 2 of them remain. It's actually m of them remains, and generally that m would be 100 or 200 or something like that, but it won't be 2 to the power n. It will not increase with system size. Okay, so the final purple big the block is not a single reference state. That's what you mean? No. Okay. It is a multi-reference state, but not exponentially number of multi-reference state. Okay. Yeah. Thank you. Yeah, Debashree, please continue. Yeah. Okay. So essentially, as I have explained just a while back, DMRG simply gives us a good algorithm to determine these matrix product states. And again, this looks like a exponential scaling and a very general answers and looks like amazingly economical and all of that. That is true as long as the dimension of the matrix product state itself is small, in the sense that as long as the 2 sides next to each other are not so strongly connected that you need to retain all the states. If you need to retain all the states, this does not give you any benefit whatsoever. Okay, another question that does not occur in most of the material context or physics model Hamiltonian context, but it will come across if you are looking at molecules.
If you are looking at molecules, you will notice that each atom has many orbitals. For example, I have this molecule over here, a pretty complicated looking molecule, but you can see there are 2 d orbital metals in the center. So you will need, it's quite rational to believe that you will need a multi-reference wave function, and a pretty big one indeed. So there are many orbitals that are present. How do we order orbitals one after the other so that I retain the least number of most efficient truncation of the matrix product state? That is a question that bothers us quite a bit. And in order to find that, we generally have to do some kind of a orbital entanglement mapping. For example, here you will see there are many orbitals, actually 13 orbitals that are present in this valence space. And among these 13 orbitals, we have found out that these dark lines are the most strongly correlated. They are strongly correlated by 0.1. The next ones are the dotted lines are 0.01, and the ones after the green ones, the many green ones, they are not that connected at all. So essentially, you basically, when you are ordering orbitals, you will start like this, maybe 4 and then 10 and then 11 and then 7 and like that. So you'll go one after the other so that all of them next to each other are the most connected ones. You should not ever put an orbital which is strongly connected with another very far away from each other, but basically then you are going to lose the correlation between them. This is a very local way of looking at correlation, but again, conceptually, that's how it is, right? 2 orbitals which are close to each other should be the most correlated, and the orbitals which are far from each other shouldn't be that strongly correlated. So with that very simple logic, we go on ahead. So these are some of the results in polyacenes, which I'll kind of not go into too much details because these are quite old results now. From using DMRG and other strongly correlated or other multi-reference methods, it can be shown that polyacenes become polyradical in nature as you successively increase the size of the polyacene. And that indeed, it is a combination of static and dynamic correlation that is together playing a role in finding the exact value of the singlet triplet gap. But what we have done very recently is change up the type of molecules a bit and looked at the singlet triplet gaps. So this was polyacenes, which have been studied for quite some time now. Now this, if we look at the polyazulenes, which are just one azulene unit stuck to another azulene unit, stuck to another azulene unit, so on. And this is the system size over here. So as we have studied from our undergraduate levels that azulene has a singlet triplet gap, which is much lower than naphthalene, we find that that is indeed the case. But on the other hand, the polyazulene actually does not decrease in its singlet triplet gap does not decrease as quickly as polyacenes does. On the other hand, if you look at this fused acene azulene rings, which are essentially a combination of the azulene and the acene. So you have a 7-membered ring, a 6-membered ring, 6-membered ring, and a 5-membered ring. And you can have many different combinations of these 7 and 5 and so on, and you can increase the size too. You see that it starts low, the singlet triplet gap, and then reduces as quickly as the singlet triplet gap reduction in polyacenes. And by the system size of 6 rings or so, it has actually crossed over. There's a singlet triplet crossover, which, if you remember, does not happen in case of polyacenes. As long as you extend it, doesn't matter. It's an exponential, yeah.
Yeah, sorry. Finish. Yeah.
It's an exponential drop off, but it never crosses over. It just plateaus at 0, very near 0. Yeah.
Thank you. So Debashree, these numbers are subtraction of the singlet and the triplet, the ground singlet and the first triplet, right? First excited triplet.
Yes.
Now, if I sort of rescale this graph in terms of ratio of the energies, how will that look? Ratio of the energies. Say, for example, the ground state has, say, some some 1 EV, minus 1 EV, and the other is, sorry, 1 EV and the other is say 1 point, so 2 EV. But the difference is what you're plotting here.
This
right?
difference is, see, absolute energies don't make much sense.
Don't make much of it.
Yeah.
Okay.
They don't make much sense because if you keep increasing the basis set, or
then all of these things will be better and better. Okay.
Yeah.
So then this is just the subtraction. Now the subtraction, what you're saying is, how do they approach each other, right? How the triplet goes down with respect to the singlet.
Yes.
Okay. So at 0 means there is a crossover, and anything above 1 EV, 2 EV. Okay. So now in terms of, because this is something which is interesting for singlet fission, in terms of singlet fission chromophores, which ones, where do we want to be in terms of the numbers?
We want to be between 1 and 2.
1 and 2.
Indeed, 1 and 2.
Okay.
So actually we started, this is a little bit of a history of how we started with this project. We were trying to get a smaller molecule, which would be a better singlet fission material, smaller than pentasine. Yeah. And indeed, you will see that this one, the 3-membered fused acene-azulene is. But what we found is that although the singlet triplet gap looks conducive, the singlet gap is not twice the singlet triplet gap.
Okay.
So that does not occur. So while it looks like we have found this amazing singlet fission material, it's not true.
Okay.
That's how we started this project.
Okay. So yeah, because we would like to look at the S1.
Yeah. So that one is not shown here, but I can show you the results some other time.
Okay, fine.
Follow the criteria.
Yeah, sure, it doesn't follow it. Okay, fine. Thank you.
So I have one question here. So, you looked at triplet, but what about quintet? At some point, even the quintet might come, lower in energy, isn't it?
It's possible to look. We haven't, but it's actually trivial to look. Okay. And we can just throw the calculations and it will do it. In fact, here is the interesting nugget of information. So the calculation of the singlet is actually harder than that of the triplet, and triplet is harder than that of the quintet. As you increase in the spin states, they become all up or all down, right? So the number of configurations decrease and it becomes less and less multi-reference.
Yeah. Thank you.
Yeah. Okay, so to summarize, we have found that the fused acene-azulenes has a much lower singlet triplet gap than polyacenes and polyazulenes, which is something we did not expect. But the next question we asked is why? Why is the singlet triplet gap of fused acene-azulenes so much lower, especially from the polyazulenes? And then we went and looked at the correlation between the diradical nature and the singlet triplet gap. This is what the correlation curve looks like, which essentially means there is no correlation. And I'm not going into too much of the details over here, but along that time, we came across this paper by Ramshesha and co-workers, where they showed the quantum phases of frustrated two-leg spin-half ladders. So this is a two-leg spin-half, two-leg spin-half. Each of them have a spin-half ladder, and they have skewed rung. So this does not look anything like a polyaromatic hydrocarbon, but indeed, whatever is the connection over here, this 7-membered ring is actually this 7-membered ring, and this 5-membered ring is this 5-membered ring, and so on. So although the title does not look anything similar to a molecular system, it is indeed one. And the reason they say that there are different quantum phases of matter, which basically means different spin states become more stable, they say the reason for that is spin frustration. So how do we go about finding out if spin frustration is indeed occurring in our systems? So firstly, we have to create a model Hamiltonian for that, a model Hamiltonian that is scaled to the properties that we are looking at in our molecular system. So essentially, we remove all the lattice degrees of freedom, that is the variations in bond lengths, and we remove all the molecular degrees of freedom and keep only the nearest neighbor interactions in the form of a Heisenberg Hamiltonian. Here, there are quite a few approaches of building a Heisenberg Hamiltonian. Heisenberg Hamiltonian, if you notice, if you have 3 sides, here we have many, many sides though. If you have only 3 sides, these are the 3 possibilities, 3 different spin states that needs to be targeted for a Heisenberg system. For a Hubbard, you will have a spin hopping, and therefore there are many more possibilities that need to be considered. Now, since these multi-reference calculations actually have access to these different kinds of configurations, we can kind of pool these configurations together and find out the coupling matrices between these configurations, and therefore use these couplings later on for a larger system. That's exactly what we have done. Similar approaches have been taken for quite some time now with different strongly correlated wave functions. We have taken these ideas, and then we noticed that in our systems, the polyacines, the polyazulines, and the fused acene azulines, these are the most important configurations. Here you see this is a nice configuration. There are no spin frustration. In other words, no 2 spins which are of the same sign have come next to each other and hating each other while staying next to each other. It's not that situation over here. But in polyazulines or fused acene azulines, there are more and more number of these different kinds of different spin states that are coming close to each other. These 2 upspin, again upspin, upspin, like that. These are coming close to each other. And these are always forming in the common bonds. And in fact, the number of these frustrations are maximum in case of fused acene azuline as opposed to the polyazulines. And that is why we believe that the fused acene azulines are showing this lowering of the singlet triplet gap, because the singlet state is becoming unstable because there's spin frustration. That's the reason. There are also some minor effects of the triplet state, which I'm not going to talk about today. I seem to be quickly running out of time. So let me explain some of the more ambitious directions we are starting to take these projects into. So when we did these calculations with the fused acene azulines and these systems, we thought of the question of extending this to a 2-dimensional system. For example, let's say we have a nanographene patch. In that nanographene patch, somewhere if we plug in a 5-membered ring or a 7-membered ring or so on, what does it do to the electronic structure? And here I'm not really talking about the geometrical structure, geometrical aspect so much, because there are going to be quite profound geometrical effects. I realize that. But let's say none of that happens. Let's say in this ideal world, we can look at only the electronic effects of these systems. What happens then? The problem about answering this question using DMRG is that DMRG is not efficient in 2-dimensional system. Again, I can write it as a matrix product state. Those matrices, each of them are going to be so huge that they won't be able to save me any computer time. The reason why that is because the entanglement entropy between a bipartite system, as in if I take a system and break it into 2 parts, that depends on the area of the boundary. So if you have a 2-dimensional system, if you cut it over here, this is the boundary of the system. This is the area. So with the system size, let's say first it was 5 by 5, then it was 6 by 6, the area keeps increasing. So with the system size growing bigger and bigger and bigger, the matrices that I need to retain becomes bigger and bigger and bigger. You can say I can zigzag through the DMRG, through the sites in DMRG. That's all well and good. That's exactly what it's done. But you lose the important configurations or the important correlation between nearest neighbors such as 1 and 10, maybe even 2 and 9, 3 and 8, and so on. So essentially, this is we are pushing the boundaries of what can be done with even DMRG. So at this point, actually, I came across a really nice paper by Carleo and Troyer, where they have shown that tensor product states are a good approximation of restricted Boltzmann machine. Restricted Boltzmann machine is actually a special kind of a neural network. Of course, I didn't know about machine learning so much at that point. So we started with a simple machine that is a simple ANN, simple artificial neural network, and tried to see if this problem is learnable, whether these matrix product states can be learned. Even before going to matrix product states, we actually tried to learn the CI coefficients. But let me first explain how the problem can be rephrased into a machine learning problem. So what we had in our hands is a matrix product state that looks like this, or rather a tensor product state that looks like this. This is a huge tensor, right? This is the full CI tensor. I need to learn what is this function. In neural nets, what a function is approximated as is some kind of a W, or which is basically the matrices, and each of the matrix elements being the weights of how much of this is carried into here or here or here. So this is W11, this is W12, this is W13, 14, 15, like that. So that's how the matrix is built. This matrix multiplied by whatever is my input with some kind of a function. Let's say a function of an input. If I multiply that with a matrix, there's a first matrix multiplication. I can have again another matrix multiplication, another matrix multiplication, as deep as you want. Doesn't hurt us. So this is what my flexible function looks like. Flexible neural network function looks like. What a machine learning problem really is, let's say I have a function y of x. I have a real function y of x. I don't know what that function is. But can I find out another function f of x that is a close representation of y of x? What do I mean by that? By that, I mean f of x has an extremely flexible structure. Having so many w's actually gives it a very flexible structure. F that is close to y for the training data. So for all the data that I have given, data being x input, whatever the known output is, if I can find that f of x is actually a close representation of that for the training data, and f of x is the simplest form of f of x that's possible. As in, I don't want to make the w so huge and so big that it can, fit an elephant. I want to make it as small as possible. So as few tunable parameters as possible. So this is essentially what any machine learning problem does. And here my y of x is actually this CI coefficient. I am going to try to model it using some f of x. So this is what now my problem is starting to look like. And instead of minimizing the energy with respect to w, so I could, let's say if this was my function, so this is essentially my wave function. If that were the case, then I can use this function as a way to compute energy by doing f of x, h, f of x, integral over d of x, and x being, many parameters, all the x, y, z coordinates. I could have done that and minimized the energy. That's what we have been doing in some way in all the variational problems. We have a wave function ansatz, some kind of a psi of x, and I optimize that psi of x, the parameters of psi of x variationally. Here, I want to do that instead of by minimizing the energy, I want to do that by mimicking the data. So the next question that one will ask at that point is, what is the data? Well, if I have a subset of the weights or the CI coefficients that are known, that I can use as the data to find out what happens in the rest of the Hilbert space. So essentially, I am stuck with the problem of minimizing a cost function, which is a difference between f of x and y of x given some w. And I'm going to minimize this cost function. So I'm going to calculate del c, del w, being each of the parameters of w. So this is how I can rephrase any variational problem as a machine learning problem. What is the benefit? Well, we don't have to compute the energy ever. What is the negative point? The negative point is I have to somehow get the data so that I can actually fit this problem. I have to somehow have access to some of the data. So we have constructed a network that looks like this. I won't go into the details here. I will just try to impress upon you that the number of parameters is actually square of the number of nodes, goes as the square of the number of nodes, and number of nodes I can fix as the number of inputs. So essentially it is a square of the system size. instead of exponential again. So instead of an exponential or a factorial number of terms, we now have a square number of terms that we are going to play around with or fit with or whatever. And we have used the spin states of each of the sites as our input. With that, here we show that indeed training of the CI coefficients and validation, if I had access to the full CI wave function, that is possible. And the prediction of psi from that has low errors. So with that in mind, let's actually see what it does if I have different kinds of systems. If I have 16 one-dimensional sites or 18 one-dimensional sites, or even a polyaromatic hydrocarbon such as a tetracene, you see that over here, you can have training errors of the order of 10 to the power minus 6 or 7, and testing errors of the order of 10 to the power minus 6 or 7. So that's pretty good errors that we can indeed see. So in fact, these CI coefficients are trainable. So what we have done is we have done a Monte Carlo on the full Hilbert space, generated a few of the configurations and generated the weights of few of the configurations. That is essentially my training space over here. With that training space energy or the training space coefficients, if I try to predict the rest of the space, you see that this is the ANN predicted energy. Here, what I have plotted is the energy with respect to subspace size. How big of a Hamiltonian, how big of a Hilbert space I don't want to consider. So this is what I had trained on. This is the data I had to train on. And this is the data I have been able to predict after training. So it's like if I have a very big space, I know only a small information about a little space. From that small information, I can actually predict the rest of the space with reasonable accuracy so that I can get the variational energies quite well with respect to the exact variational energies. That's what we did in this work. But again, around that time, we looked at another paper which said that in fact, not only CI expansion, but matrix product states itself can be learned. CI expansions, as you know, are anyways exponentially scaling number of coefficients. So I don't want to learn exponentially scaling number of coefficients. I want to learn only a few coefficients. And the algorithm to achieve that is in fact very close to a DMRG algorithm. So this paper over here, they actually use this to predict handwriting. I mean, to understand handwriting, you know, digits on a handwritten digits. So we have actually used that to learn the matrix product states of a physical system. And again, the importance of the yes, I will finish in 2 minutes.
Okay.
I'll finish in 2 minutes. I have the watch right here. So, so the benefit of optimizing MPS variationally versus with machine learning is the following. If I have an MPS and if I want to calculate its energy, this is a computation that looks like this, which in the picture it looks like over here. And so the computational scaling of that with the system size, K is the system size, is if I have an MPO based algorithm, it is K to the power 4. If it's a DMRG algorithm, it is K cubed. On the other hand, if I do the same using machine learning, this scales as K. You might again think it is a fantastic, but please note that K is multiplied to the number of training data. And we really, by we mean the whole scientific community, including the computer science literature, doesn't know how the training data increases or remains same with the system size. So we don't know how NT scales with K, but given whatever number of training data, actually the scaling is linear with respect to the system size. So that's indeed a big saving even from DMRG algorithm, which in my opinion is anyways a very fantastic algorithm. Here we have shown in the right-hand figure, left-hand figure, let's forget about it for now. In the right-hand figure, we have shown the energy. So the black one is the CI energy, the full the ANN CI energy, which we have originally shown that it's quite accurate with respect to full CI. And the red one is the MPS energy with number of M or bond order that is kept at 75. If you decrease the bond order, of course, your computation is much, much faster, but there's no free lunch. So the errors also increase. So indeed, it is possible to optimize MPS for a physical system, such as this tetracene. This is a test case on tetracene using machine learning, and that we believe is a better scaling with respect to system size than variational optimization. That's really all we had to do, all we had to say over here. And I'll not go through each of the conclusions, but I will go through the acknowledgement, because all of this work has been done by the 3 students, Madhumita, Sumanto, and Mondira. And much of the work, in fact, the first 2, Mondira is just joining in. And thanks to the rest of the group and funding agencies and so on for making all of this work possible, and also IACS. And thank you all for listening to me. Thank you.
Thank you very much, Debashree. That was fantastic. So if the audience can unmute themselves and give a big round of applause. Thank you, Debashree. So the talk is open for further questions. So I invite members from the audience. Yes. Okay. Vamsi?
Sorry, I was actually just applauding, but I have a question.
Okay.
So you have developed all these nice methods. I know these are initial stages, but how close are you, say, for example, to make them user-friendly? So if I were to just...
we are trying very hard. That's the truth. Yeah, these are not user-friendly at all at this point. These are a mess.
But do you see them? To say that. Yeah, do you see them reaching that stage? I mean, I'm just asking a very...
So I have an NSM project that is involved with making them kind of user-friendly. And yeah, we are trying. Some of the code we have actually opened in GitHub and all that, but still not a very user-friendly way of putting it. But the rest of it is a serious mess.
Okay.
Maybe in a couple of years, because I'm right now taking a lot of project students and so on who might make these into GUI based and stuff like that. So that will probably keep some of the mess out of view of people, out of sight, out of mind.
Yeah. Okay. And I have one more theoretical question, which is, when you, machine learn the full CI energy using a few CI coefficients.
Yeah.
Right? So there I'm wondering, like, how do you, suppose you have degenerate states, for example, how do you ensure that, for example, the final wave function is an eigenfunction of S square, for example? Does it still come out?
Yeah, that's a very good question. The results that I have shown is without doing that, but now we have a way of even state targeting. So at each iteration, we purify the state.
I see. Okay.
Yeah.
Yeah. Okay. Thank you.
That is actually in the works, and yeah, it makes it a bit slower by a factor, let's say 2-3 times, but it's still doable.
Okay. Yeah. Thank you. Yeah.
Thank you, Vamsi. Chandan?
Yeah. So I have one small question. So you started by talking about this excited state and strongly correlated electrons. So this pH molecule has these delocalized pi electrons, which are highly correlated. So, and they because of these highly correlated electrons, they exhibit this collective excitation, which are also known as this plasmon excitation. So are you able to calculate those as well in this?
For single molecules or dimers, yes. For more than that, no.
Okay. So like single molecule, so single pH molecule. So are you able to calculate this plasmon excitation state?
Yes.
Is it?
Yes.
Okay.
That is actually not difficult at all.
Okay. So that's actually very interesting, because we try to look at this plasmon excitation state from the experimental point of view, from in the electron emission channel. So
yeah, see
okay.
here there are actually the artifacts that DFT has. When you calculate much of the plasmonic states, they have charge transfer in them, right? And DFT fails miserably for this. We don't have any of those issues. So
Okay.
there it's actually pretty simple. For for dimers, it becomes not just computationally more expensive, it becomes analysis of those results become quite messy. For more than dimers, I have never tried. I am scared. I have really never tried.
Yeah, that's fine. Okay, thank you so much. That's helpful. I may write to you a bit
Sure,
more
I will
about
be very
it.
happy to. Yeah.
Sure. Thank you.
Thank you, Chandan. Any other questions? Okay. Well, if there aren't any, okay. Oh, sorry, Ravi. Ravi was clapping and then his hands.
Wrong reaction. Yeah, wrong reaction.
Okay, Ravi, please. Sorry.
Yeah.
Hi, how are you?
Yeah, Debashree, great to see you actually. I joined a bit late. I had another meeting actually, but yeah, always a pleasure to hear you. So I was just wondering, we spoke actually some years ago actually, but I was wondering in terms of the DMRG approaches that you're mentioning, plus you have now these machine learning strategies, etc. So what is the status quo at this point in terms of treating larger systems? For example, I don't know in the first part of your talk whether you covered anything on proteins or biological
I
molecules.
mainly talked about only strong correlation. With DMRG, we can go to really large systems, of course, and we are doing these calculations on singlet fission material and stuff like that. Again, by material, to me, a dimer is a material. So that's the limit as of now. But, DMRG can be used with MM. That's not a very big issue because you can just get the 1 and 2 electron integrals with an MM and then use that for DMRG. We have done that before.
So by MM, what do you mean actually? MM is?
MM, by that I mean just point charges. So if I have a point charge, essentially I'm giving a perturbation in the 1 electron part of the Hamiltonian, and that changes my 1 and 2 electron integrals. I take those and then do DMRG. That's not a very, it's then essentially your QM does not see the M. QM does not influence the MM anymore. It's a one-shot method that can be done. More than that,
So right now, in terms of number of atoms, actually, when you say dimer, what do you mean by number? How many atoms are you talking about at this point?
We can easily go up to 150 or so.
150 or
yeah.
Okay. Yes. Okay. Anyways, we'll talk a bit later, so I can actually talk a bit more. Thanks.
Okay. I guess. We don't have any further questions. So let's thank once again Professor Debashree Ghosh for a wonderful online visit and very nice colloquium explaining DMRG as well as multi-reference methods in general. So thank you, Debashree. That was very nicely done. The other thing that I would like to tell the audience is we will continue next week with Professor Amitesh Anand, who is actually a faculty within TIFR in the Department of Biological Sciences. He's going to give his introductory talk as he joined maybe 6 months back. So we'll hear a little bit biology next week. So we look forward to another exciting session. With that, I would like to also thank the lecture theater folks who kept the talk open for a wide viewing in the lecture theater, that is AG66, where Debashree would have given the talk had she physically been there in here. So sorry, Debashree, but next time we'll have you for lunch. Okay.
Yes, sure. We'll love to visit you guys.
Yeah, we're here for lunch. Yeah, sorry. So now I would like to close this session right now, but Debashree and Ravi and Vamsi, please stick around because this is the same Zoom link that we will use for the private sort of meetings. So